let's talk about power. So, what is power in physics? Well, power is has the unit of watts, and watts can be just represented by W. Do not confuse this with work. Work and watts are different. They're both represented by W, which is kind of bad design, but these 1950s physics scientists chose these names, so okay. But what is a watt? Well, a watt can be calculated by finding the joules of work over seconds. So joules is work here, and seconds is your change in time. So if you were to calculate power, you would just put work over the change in time. And for the people that are taking calculus-based physics, work is equal to the power with respect to time, the integral of power with respect to time. So that's just an identity that you can have. But power overall, very easy concept to understand. The unit for power is either watts or joules over seconds. But if you use joules over seconds, it basically gives you the formula for calculating work, since the unit for joules is work or energy, and seconds is just time. So this right here is just the formula in itself for power. So for this problem, we need to calculate the power and the power of some electric motors that are pulling up on an elevator in the Burj Khalifa. So these elevators travel 412 meters in 60 seconds. This is probably not the real number, but it's just made up numbers. So we travel 400 meters, so change in height is 412 meters and 60 seconds. So your change in time is equal to 60 seconds. And your mass of the elevator is 2,000 kilos. So if you were to draw some representation of this elevator, you would draw a box, and you would have a weight force, and you have a tension force of some ropes pulling up on this elevator, or some force. So in order to calculate the weight force, you just need to multiply mass by the gravitational constant on Earth, and you get a weight force of 19,600 newtons. But since the elevator travels at a constant speed, your net force is equal to 0 since there is no acceleration. Therefore, your tension force is also, so tension is also equal to 19,600 newtons. Now this tension force is caused by the electric motors pulling up on it. So the electric motors need to exert some work through this tension force in order to pull the elevator upwards. So the reason why I'm talking about work is because in order to calculate power, you need to do work over change in time. Well, we have the change in time. Change in time is already given here with 60 seconds, but we need to calculate work. So how do you calculate work? You can calculate work by just multiplying the force of the tension times the displacement. And the reason why I'm not including the cosine value here is just because your tension force and your displacement are going the exact same direction. So both the vectors are going the exact same direction, but the real formula for work contains a dot product, which has a cosine value in it. But once you calculate this, your work is approximately 8.1 megajoules. Now, if you don't round, you would get about 75 megajoules. But I rounded here. No big deal. Usually physics exams will give you full credit even if you round midway. And once we found the work, we can find the power. Since the formula for power is work over change in time, we just need to set up that. And once you've set up the formula for work over time, your power is equal to 0.134 megawatts, which is also approximately 134,000 watts. So your electric motors must exert a power of 134,000 watts in order to move this elevator. So for this problem, you have a man of mass 80 kilos. And he runs up a flight of stairs 20 meters high. So we have the mass written down, 80 kilos, and we have the change in height, 20 meters. These are all important details. We also have our change in time, 10 seconds. How much power is used to lift the man? So first we need to find the amount of power to lift a man. The formula for power is, remember, watts over change in time, as the unit is just joules over seconds for power. So, oh, not watts, work over change in time. Oops. So how much power is used to actually lift the man? Well, we first need to find the work done by the man, and the work done is just against gravity. So against gravity, so the weight. So maybe I should put force of Earth for this rather than another W to make this more confusing. So the force of Earth is just equal to the mass times gravity. So mass times gravity, and the weight force is equal to 784 newtons. Therefore, the person, in order to go up, has to exert 784 newtons if he's at a consistent speed, which is what you will always assume if they don't mention any acceleration in these types of problems. But now that you have your force and you also have your change in height, you can find the work. So now that we have your work, by multiplying your force by the change in height, you get a work of 15,680 joules. So you have your work and you also have your change in time, so you can just divide your work by the change in time to get power. And the power is represented by watts. So the actual wattage used in order to lift the man up 20 meters in 10 seconds is 1568 watts. Now, here's the thing. In real-world situations, not all the energy you use will go into movement. A lot will dissipate into heat. A lot will be into sound. I don't know, keeping you alive. I don't know. There's many factors in real life that kind of make things less efficient. So the energy you put into something is less efficient. So if the man's body is 25% efficient, how much power does it expend? So 25% of the actual power you're exerting goes into the activity. So if 1568 watts is needed, is just 25% of the total amount of power exerted by the person. That means that 1568, actually I'll put parts. This is A, this is B. 1568 watts is just equal to 25% of the, so 0.25 of the total power. So if you divide 0.25 by both sides, you get a power of 6272 watts actually used by the man, assuming he has a 25% efficiency consistently. So out of this 6272 watts, only 1568 of it, of the power that he's using, is actually going into his movement. The rest going into something else. So how long will it take for an 850 kilo car, so this is important, 850 kilo car with a useful power output of 40 horsepower. So we need to do some conversion, 40 horsepower. And this unit of conversion just gives us the canceling of the horsepower unit, and in the end we get a power output of the engine of 29,840 watts. Let's make this 8 a little better. So how long will it take to reach a speed of 15 meters per second neglecting friction? So assuming this is on a flat surface, so there is no incline or decline, we need to solve for the time it'll take in order to get to 15 meters per second. So how do we do that? Well, this watts is equal to joules over seconds. So power is the unit of joules over seconds. So in order to calculate everything that we need to solve for the kinetic energy, or the change, or the work, or the change in kinetic energy in order to get to 15 meters per second. So let's set up the kinetic energy formula. And This is the kinetic energy formula, 1/2 times the mass of the car times the speed squared. So this is our kinetic energy. Is actually more specifically our work, or the change in kinetic energy, since the car starts at rest. So this is the work of our car. The engine needs to exert onto the car to reach 15 meters per second. So once we have this work, well, we can set up a power equation. So power is equal to work over change in time. So if we were to set up the equation specifically for this problem, you would have a formula that looks something like this, where our power of the engine is on the left side of the equation, and our work is on the top, or the numerator of this fraction here. So with doing just a little bit of algebra, you can solve for the change in time in this case. So the change in time is equal to 3.2 seconds. So in 3.2 seconds, a car with 40 horsepower can reach a speed of 15 meters per second within 3.2 seconds. Now, in reality, you're not gonna get that 100% efficiency in this case, so you probably need more power. But let's solve for part B. So for part B, you have an kind of incline now. So you need to gain 3 meters in the process. So in order to gain 3 meters, well, you need to resist against gravity. So let's solve for the gravitational force of this car. So the gravitational force of this car is equal to, or the weight is equal on the, oh my god, the gravitational force on the car, not of the car, is equal to 8,330 newtons. So we can actually calculate the work needed to lift the car up 3 meters given a force and a height change. So the height change is equal to 3 meters. Our kinetic energy still stays the same as the car is still going the same speed. So we just need to use the same kinetic energy. So the kinetic energy is still 95.62 joules. So your kinetic energy is still 95.62 joules. And since you start from rest, this is technically your change in kinetic energy. Or more specifically, your work. So now that we still have the same kinetic energy, and we have our force of gravity, we just need to calculate the work the engine needs to do onto the car in order for it to go up the hill. So in order to calculate that work, well, you have a force and you have a height. You can multiply these two together. And when you multiply 8,330 times 3 meters, you get 24,990 joules. So this is the amount of energy it needs to take to lift your car up 3 meters, and this is the amount of energy it takes in order for your car to travel 15 meters per second. So if you add both of these together, so you add 95,625 plus your gravitational energy, you'll get a total required energy of 120,615 joules. So this is more than the previous one because you're also going upwards. So you need to resist against, the car needs to resist against the force of gravity this time instead of just increasing in velocity. So when you're going up a hill and you're trying to increase your speed to 15 meters per second, you require more energy due to the fact your car has to resist gravity as well, or your engine has to resist gravity. So now that we have this, we can set up our power formula. So power is equal to work. Let's stay within our parameters. Power is equal to work over change in time. And since your work is your change in energy here, this is the work that your engine needs to do onto the car, you can set up the equation like so, where the work is at the top of the fraction at the numerator, as that's what the formula states in order to calculate power, and your times at the denominator of this fraction. Since you're using the same car, your power of the car will still be the same, 40 horsepower, also known as 29,840 watts. So with just a little bit of algebra, again, you can isolate your time variable, and once you isolate that, you get a change in time of 4.04 seconds. So it takes more time with the same engine because you need to deliver more joules in order to change the position of the car upward in part B. So, as always, I need to mention that I get these problems from OpenStax. Great textbook. It's an online textbook. But, as always, if you have any questions, put it down in the comment section. I hope this video helped.